Okay, let's start today's class. Today we will talk about SPI, serial peripheral interface. Do you remember SPI? Actually, I give you the homework one. Let you to do a research about what is SPI, I2C, UART, like that. Do you remember? So before we start today's class, do you know what? Do you remember what is SPI?
It's a communication protocol.
Yeah, it's a communication protocol. Yeah, actually, yeah. Today we will use SPI to try to transfer data, receive data, using some specific rule. Yeah. Okay, let's start today's class. Okay. Do you remember lab 4? Like we use ADC chip TLC 0831 to read the data. Do you remember that? Yeah. Okay. This is what we talk about. This is the chip, and this is the potential meter. And as we adjust the potential meter, and the voltage will change, and then the ADC chip TLC 0831 will read the specific voltage, transfer it to the binary, and then read the output the binary, give the output to the pico. Do you remember that? Yeah, and then this is what we talk about. We will give it a clock, and right there is a CS. CS is just like a what is CS? Do you remember?
Chip select.
Huh?
Chip select.
Yeah, chips select. Yeah, just try to make the chip is working like that, and then we read the data, and this is our code. Actually, we try to make a clock using the code. Am I right? Do you remember? Yeah, I think yeah, the Xander will remember because when you use C++ and the because of the speed thing, and yeah, actually we call this software SPI, also bit banging like that. Yeah, then let's talk about what is SPI exactly. Actually, you can see the SPI, like we talk about, it is a synchronous, how to pronounce synchron, how to
Synchronous.
Oh, synchronous. Yeah. I repeat it again. Still synchronous for duplicate communication protocol. Yeah, actually for this protocol, we usually have a master device and then several slave devices. Yeah, and this is a synchronous, which means the clock will give the master and the slave a working rate, working piece, and those master and the slave will work at the same time. Yeah. Then for the SPI, there are some do you remember this pin? Like I think you have already finished several labs, and right when you connect your pin, you need to check which pin you need to connect. I'm right. So for the GP, it's just general input output. You have already used it many times. I'm right. And so far we just use the general output input function. I'm right. We just try to define pin. Also some PWM, but you can see when you observe the pin, you can see it also will they are labeled as SPI, the purple one, and the blue one I2C, and this is dark purple. This is light purple. Yeah, it's also purple. And which means what does that mean? Which means those pins can be used as a general input output. Am I right? Pin. Also, it can be used as a SPI LAN. Am I right? Usually, you can see for the SPI, you can see there are 4 different LANs. We call it LANs, like different pins you can use. Am I right? So those are different pins. You can see here are 4. Am I right? Also here are 4. Like those are just these 4 are therefore you see it in the like image in that image. Yeah. So you can see one is MOSI, master out slave in, which means this line used by the master to send data to the slave. Okay, just tell me which is MOSI. Do you know? Huh? Like we know like here there are 4 different pins as can be used for the SPI like communication protocol, and here also those 4 are just those 4 are just that 4. Yeah, so we just talked about MOSI, which means the master out, slave in, which means the data will be sent by the master and will received by the slave. And correspondingly, which one is MOSI? This is my question.
Probably the TX.
Yeah, the TX. This is just like the transfer date, which means I just this is a T, am I right? Actually, here is R, which means receive data. I just receive the data from the slave. Yeah, that makes sense to you? Yeah. So which means like the TX is just master out, slave in. It's just the line used by the master to send data to the slave. And the MISO is master in, slave out, which means the line used to transfer data from the slaves to the master. The master will receive the data. That makes sense to you? Yeah. Do you have any questions? Oh, sorry, I think. Okay. And the other one is clock, theory clock. Actually, this clock signal is generated by the master to synchronize data transfer. So which one is clock? SCK, yeah, that's right. The other one is just SS or CS. It's just like the sleeve select or chip select. It's just like a, sorry. Yeah, a line used by the master to select the desired slave device for communication. Actually, you can see those software SPI is just similar with the hardware SPI we talk about, am I right? It has a CS, it has a clock, am I right? It has a data receive or data transfer. It depends on your code, am I right? So this we call it software SPI. It's just like we use code to implement SPI. That makes sense to you? And this one is just hardware. We just use some like a specific circle to implement this function. That makes sense to you? So we call it hardware. For the data transmission, there are different ways. The first way, we call it two-way data, which means you have master device and you have slave device. And your data can be transferred from the slave to the master to the slave. Also can be transferred from the slave to the master. It is two-way, am I right? And then there is the other way, is single way, and which means your data transmission is just from the master to slave. Yeah, it depends on your configuration. Okay, this is just what we talk about. Actually, I want to ask you a question. We talk about the SPI, am I right? Did you observe the I2C and the UART before? You can see the SPI. Actually, I just put a part of the Pico. If you observe the whole picture of Pico, let me open that for you. You can see there are different group SPI, right? Actually, those different group has the same function, but you can use different SPI like pins to connect to the different devices and then do something, am I right? And let's try to observe I2C. Did you notice the I2C? How many will be one group? Are you sure? How many? Yeah, two. Which means for the I2C, you just need to use two, like as one group. One is SC is just like a clock signal. DA is just data, which means I2C is also synchronous, like a protocol, which compare the SPI and the I2C. Do you know the big difference? Huh?
Is it just the iPhone version of the
Uh, Yeah. Actually, yeah, you're right. And also, you can see compare with the SPI. The SPI has four, and the I2C only has two. If you just want to use fewer wire, you can use I2C, and also the I2C can connect multiple devices. Yeah, and also the UART. Actually, the UART is just asynchronous. It's not like a synchronous. Yeah, it's asynchronous. And then the UART also have two, only have two. Am I right? One is receive, the other is like a send. Yeah. So actually, the different communication protocol has different function. What do you need when you try to connect the sensor or connect other devices? You need to decide which protocol, which like communication protocol you need to use. Yeah, this for our lab, you don't need to worry about these things. But for the final project, we want to connect the sensor, we will connect other devices. You need to choose the proper like communication protocol. Yeah, I just want to talk about that. Any questions so far? Yeah, which means if you want speed, actually the SPI is very fast. If you want fewer wires, the I2C you can choose. If you want a simplicity, like the UART, you can choose. Yeah. Okay. Then we have already finished the lab 6 labs, and then you remember how can we use the pin, the Pico pin as a general input output? Do you remember? How can we use the pin as a general input output? We just use code, am I right?
Yes,
Yeah, to try to define it is a pin, like use some code, define it is a pin, and pin is just the general input output. But if we want to use these pins as a SPI, there are some different code you can use. Okay? Oh, sorry. I need to close it. Yeah, this one. You can see here, you don't define the specific pin as a like a just regular pin. You need to use the SPI function. The SPI function will like define your like pin 18 is just a clock, and your pin 19 is just a MOSI, and your 16 is MISO. Yeah, use this code to define your pin will be like used as a SPI communication protocol. That makes sense to you? And then you can see here the ID. There are some like parameters. The ID is just specific to the SPI channel, can be 0 or 1. And the bird rate is just the frequency, you like your clock's frequency. And the polarity is just clock polarity. If you set it to 0, the SCK output low when idle, otherwise it outputs high. Which this if the polarity and the phase will decide when you will read the data in the high region or like a high region edge or like the low region edge. Yeah. And the freeze is clock phase. If you set it to 0, data is captured on the first clock edge. Otherwise, it captured on the second clock edge. Yeah, and the bits is number of data bits transferred per cycle. And the first bit determines whether the most significant bit or least significant bit is transmitted firstly. Do you know what's the most significant, or what's the difference between the most significant bit and the least significant bit? Do you know? Yeah, the most significant bit, which means your SPI will read the first bit will be the most significant. For example, your binary number is let me. Yeah, your binary number is 1100. The most significant bit, which means this one will be read or input or output firstly, and the least significant bit, which means this bit will be read or output will firstly. That makes sense to you? Yeah, just pay attention to that. And then here are some functions you can use. Yeah. This is the initial. You can see initial the SPI, and this is after you finish using it, you deinitiate and read it and read date and read into which means you read the data into the specific configuration, and this is write, and this is write read into. Oh, I need to put all function there, but okay. Yeah, but don't worry about this. And I have already give you the code for this lab, and you need to pay attention on how to use different functions, how to use different configurations. Any questions so far? Okay, and then let's talk about the lab 7. Yeah, for the lab 7, you will understand what SPI is. And also you will connect TLC0831 using hardware SPI. We have already used TLC as a software SPI. And then you try to compare SPI with software SPI. Yeah. And analyze timing using oscilloscope. Yeah. For today's lab, you need to use the oscilloscope to detect the signals. And then investigate bird rate limits. Yeah, which means the clock frequency limits. You need to try to change the bird rate and then find the result for that. And then this is just the different communication. Okay, let's try to. I need to cover it. What is SPI? Actually, we have already talked about that. It is just a communication protocol. And actually, it is developed by Motorola, in 1980s. And the key idea for the SPI is just the date and the clock center together at the same time, which means it is synchronous. Yeah, does it make sense to you? Yeah. Any questions so far? Okay, and then why synchronous? Yeah, I need to cover this. Actually, you can see the SPI has data line, also it has separate clock line, and you can see you can receiver samples data on rising edge or falling edge. It depends what? It depends on your configuration. This one, freeze. Yeah, if you set the freeze to 0, it will be detect on higher edge, if like a rising edge. And if you set it to 1, it will be the following. It will detect the data in the falling edge. Yeah, and clock ensures master all the peripheral stay synchronized. Yeah. That makes sense to you? Yeah, this is just why we use synchronous, because we want to receive data and make the slave and the master work together at the same time. Yeah. Okay. Actually, have you ever heard a controller or peripheral before? Yeah, actually, this master slave MISO, MOSI, and SS is like an old name, traditional name. And some in some documents, they will not use this name before. They will not use this, and they use this name to replace this name. And the master will be changed to controller. The slave will be changed to peripheral, and the MISO changed to POCI. This is just similar thing. Yeah, and the MOSI changed to the PSU, and SS changed to like a chip slash. This is slave slash. This is chip slash, but it's the same meaning. Do you know why? Why the name is changed? Why we want to change the name? You know? Yeah, actually, some documents now they still use MISI. I don't know if you like notice that, but some documents they just use POCI and PSU, but it's the same meaning. Yeah. Do you know why? Why we change the name? Have you ever heard this before? No? Yeah, actually, you know, like the master slave wording can carry negative historical and social like meaning. Yeah, so that's the main reason why we don't use like the master slave again anymore. Yeah, we just use controller, peripheral, PO. So when you read some papers, when you read some like documents, if you see those two, and it's just a similar, not same, just a same meaning. Yeah, for the specific thing. Yeah. Any questions so far? Okay. And then, okay, how this relates to what we did? Like I said, we have already used the software, like some code to implement SPI like proto, am I right? And we use code to like enable the CS. We use code to create a clock, am I right? And yeah, we already did like a manual GPIO tolerance and toggling, and clock pulse generation and reading data bit by bit. And that was software SPI. And then we need to use hardware SPI peripheral. Yeah, this is just I want to compare those two again. Okay. Okay, let's try to review TLC 0831. Do you remember? We have already used this before, right? About the TLC 0831, what you can remember?
Oh, it's the little chip that you plug it in wrong, it burns your red.
Yeah, that's true, that's true. Like, what's the main function for this chip?
Analog to digital conversion.
Yeah. Analog to the digital. Yeah, he will read the voltage and convert it to the binary number. Yeah, and then read by the pico. Okay. Yeah, it is a 8-bit ADC, and also it is a MSB first. What is MSB? Actually, I just talk about it here. Like a most significant bit. Yeah, it will read the higher bit firstly, and then step by one by one. Yeah, so you need to pay attention to that. And also, yeah, the max clock is 400 kilohertz. Yeah, this is very important. Like in the lab, in today's lab, you will try to adjust this clock frequency. And from the 50 kilohertz to the 100 kilohertz, the maximum is just 400 kilohertz. If you just don't like over this number, yeah. And there is no minimum clock, but you cannot set it to the negative. Yeah, it's meaningless. Okay, the chip waits a few clock cycles before sending data. Yeah, this one actually is very important. Yeah, I will talk about why why this is very important. Okay, for the hardware setup like the wiring connections, and the CS will connect to the GP17, and the clock will connect to the GP like 18, and the do will connect to the GP16. If I just connect do to GP16, what does that mean? What does that mean? Which means I use this one. What does that mean?
You have the pins, I don't know what else to say.
Which means I just use Pico as a master to read the data from the sleeve, from the TC TLC 0831. I'm right? Yeah. So if you want to like send data using Pico, here you need to connect GP like 90. I'm right? That makes sense to you? Yeah, actually, in the code, in your code, like I just set the 18, 19, 16. You can use other group. Yeah, because we have different group for the SPI, am right? So you can use different group, but just try to pay attention. In the clock should be the connect to the clock, the CS should connect to the CS, and the output should like the input input should like connect to the RX. Yeah, pay attention to that. That makes sense to you? Any questions? Okay, and the potentiometer will connect to like a V in to the TLC 0831. Yeah, 31. Yeah, and this is just a connection. Yeah, actually, the hardware, the wiring connection, I didn't put it in the lab instruction, but the circuit is the same with the lab 4 when you use the TLC as the software, like a software SPI, it's same circuit. If you don't remember it, just review the lab 4 instruction. That makes sense to you? Okay. And then let's talk about let's review like the SPI configuration. Yeah, actually you can see this is your code. And the baud rate, we know it is clock speed. What is clock speed? It's just frequency, the period. And the polarity and the freeze, it will decide the clock mode, which means when I just set polarity at 0, which means when the Pico is idle, the output is always 0, it's always low. And if I set it 1, it's always high. If I set the freeze 0, I will read data when the reason edge. If I set it 1, I will read data in the falling edge. That makes sense to you? Yeah, which means these two decide the clock mode. Okay, let me ask you a question. For now, I just set polarity 1 and freeze 1. And what is my clock mode?
It's gonna be mode 3.
Huh?
It's mode 3 for polarity 1 and phase 1.
Yeah, which means if you don't if your Pico is idle, and the input is always high, and when you read data, you just read data when the in the reason edge. That makes sense to you? Yeah, you need to pay attention to that. Any questions so far? Okay, and the base is just a packet length. Okay, let me ask you a question, and I will talk about it later. Yeah. Okay, and the MSB first. Okay, what is MSB first? Let me ask you again.
It's
Yeah, significant. Yeah, significant bit. Will be the most significant bit will be the first one. Yeah. Okay. Any questions so far? Okay. Let me ask you a question. Here, we know the TLC that chip is 8-bit. Am I right? But why here the bits we set 10? The packet length, why we set here? Why we set 10 here? But the TLC chip is 8-bit. Do you know why? Do you guess a little? Huh? Yeah, I think you maybe get the point. Yeah, because you can see the TLC like outputs 8-bit, but the first 2 bits are actual zeros because the SPI like library reads immediately. Like you can see when you want to on the like on the pin or the off the pin, it has a time delay, but the chip delays data output. Yeah, so 2 downlink bits and plus 8 valid bits is 10 bits. Yeah, when you do the lab, just pay attention to that. Yeah, any questions so far? Okay. And then this is what you will see in today's lab. Actually, you will observe, like you can see here, this is your CS falling edge. After you CS, this is your CS, the yellow one. After your CS from the high to low, and you need to read the bit, am I right? Now you need, and the SPI will read, try to receive the bit, am I right? But you can see here, which one is CS? Which color is the CS?
The firstly yellow.
The yellow?
CS, right?
Yeah, CS is yellow. Which one is clock?
It's the third one or second one?
Yeah, anyone? Which one is clock? You're right.
The
Huh?
purple.
Which one? Huh? Yeah. Let me give you, one is blue, one is purple, and one is yellow. Yeah, that's me easy. Yeah. So which one is the clock? Purple. Yeah, because clock should be one like a hello in a specific frequency, am I right? And which one is data?
That's the blue.
Yeah, blue, am I right? And if you observe carefully, you can see the first 2 clock, there is no data read, am I right? Which means it is 2 downlink bits, 0. That makes sense to you? Yeah. So this image is is what you will observe in today's lab. Yeah. And then the CS is just enable the data reading. Okay. And let's try to, okay, here let's try to compare the image from oscilloscope and the data sheet timing. You can see here, this one is what we talk about in lab 4, am I right? This one is the ideal situation, am I right? And this one is your observed from the oscilloscope. You can try to compare those two. Yeah, and you can see the data starts after several clock pauses. And actual zeros pair first. You can see this is the ideal one. This is a real situation. Yeah, you need to compare those two. That makes sense to you? Any questions? Okay. And then, okay, what in today's lab, you will try to increase the band rate, which means the clock frequency. The start will be 10 kHz and increase gradually from like 15, 100, 200, 400. And you will think about one question. Can it really reach 400 kHz in practice? Yeah, when you try to, we know, we have already talked about the maximum frequency is 400 kHz, am I right? Yeah, so try to set it 400 kHz and try to observe, can it really reach 400 kHz in practice? Yeah, and then tell me what. Is that okay? And then other question, does data remain stable after you try to reach 400? And does oscilloscope waveform degrade when you set it 400 kHz? Yeah, when you try to adjust it to higher frequency to higher. Yeah, you need to observe when you try to increase your frequency, what will happen? That makes sense to you? Okay. And then this is just the hardware SPI and the software SPI compare with each other. You can see from the speed, like the software, actually it is slow. Yeah, I think the Xander has a strong feeling for that. Yeah, with Xander. Yeah, we compare the hardware SPI and the software SPI. For the software SPI, the speed is very slow. That's the reason why when you use C++ and you need to delay. Yeah, but you can try. You use hardware SPI. Yeah, it will faster. And for the CPU load and the software, it is high. But the hardware, yeah, you can see you don't need code. I mean, you don't need to use code to set the clock, other things. So the CPU load will low. And the precision and you can see the software SPI. You need to when we need to set the clock. It's not very accurate, but the hardware is very accurate. And the software is simple. You can see you just use several sentence code. You can implement the software SPI. But for the hardware, you need to do many configuration here. Am I right? Different here, different configuration. Am I right? Yeah, so that's the difference between the software SPI and the hardware SPI. Okay. Yeah, why use SPI? Yeah, because it's faster, cleaner timing, more reliable, less CPU overhead. And actually, many real systems will use SPI as a communication protocol. Yeah, for example, displays, ADCs, sensors, SD cards, it all use the SPI communication protocol. Yeah. Any questions so far? Any question? Okay. And this is today's lab's demonstration requirements. Yeah, you need to show SPI working. And also you need to show oscilloscope traces and explain timing. Yeah, and try to vary bound rate like that frequency. And try to determine max stable frequency. Yeah, because we know like the maximum is 400, but you will see you can now adjust it to the 400 because some reasons you will notice you need to summarize it and determine max stable frequency. Okay, this is what we will do for today's lab. Any questions so far? Yeah, actually today's lab is now that complicated, but just the theory, you need to understand what is SPI. It's just a communication protocol, which means when I will receive the data, when I will send the data, am I right? Yeah, and when I receive the data, when I start to read the data, yeah, this is just some rules for communication between the one device and the other device, like that, the master and the slave, the controller and the peripheral. Yeah. Okay, any question for today's lab? No. Yeah, for today's lab, we still start from 1 o'clock. Yeah, and yeah, if you okay, then final project. Yeah, at the beginning of this class, we talk about the final project will have a the proposal due for this Sunday. Yeah, I think. So you need to talk about what items you will need for your final project. Yeah. Okay, we have 10 minutes. Yeah, 10 minutes, and you can talk about like what items you will need for the final project. Yeah. Hey, honey, you know like which is your yeah. Okay. So your team is John and Will. Yeah, you can talk about. I think Angela is not here. Uh,
Oh, the brain and like brain input.
yeah, any question, just let me know.
Okay, yeah, so.
It's a-
I don't think so. No, it's in my son. Oh, it's not. Very Oh, so.